Hey everybody, Trey here. Welcome back to another video. Back with another case study today, and I have been asked quite a bit to cover this event in a case study video. And, I've had some other video ideas and kind of pushed this one off, but wanted to do this case study on the super outbreak from April 27th, 2011. A tornado outbreak that has really set the bar, at least in modern history, for tornado outbreaks. 199 tornadoes occurred on this day across much of the southeast, focusing on Mississippi and Alabama. And, pretty much any meteorologist knows about this day and its impact. Some of the stats from this day are just incredible. Of course, we know of the famous ones. Of course, the Tuscaloosa Birmingham EF4 here, which that was covered so well by meteorologist James Spann there at ABC 3340. The huge monster EF5 that tore through Hackleburg and Phil Campbell, Alabama. The Philadelphia, Mississippi tornado. The Smithville, Mississippi tornado that happened to toss a Ford Explorer 900 meters into the Smithville water tower, denting that water tower, and the car ended up as a mangled mess, a ball of steel in a ditch a quarter of a mile past that water tower. So just some unreal stats from this day. 90%, about 90% of all supercells that occurred on April 27th, 2011 produced tornadoes. And that is just almost unfathomable. It's hard to put that into context. Trapp et al. 2005 did a study showing that about 25% of supercells produce tornadoes. And on this one day, 9 out of 10 supercells produce tornadoes. That is just unheard of. And so, this is going to be a really in-depth case study on the meteorology of this event. I'm not going to go in depth on every single storm, the chronology so much. That would make this video really, really long. But this is going to be a deep dive into the meteorology behind the event, looking at why, what ingredients came together to produce such a prolific tornado outbreak. And then at the very end, we're going to compare the environment that produced the April 27th event to what was previously known as the gold standard for tornado outbreaks before 2011, and that was the April 3rd and 4th, 1974 super outbreak. So we'll take a look at the environment from the April 27th event and compare it to the April 3rd and 4th, 1974 event. And sneak peek, we're going to see quite a few similarities in the two environments, showing you just how perfect things need to be for prolific tornado outbreaks like this to occur. Just a quick note before we dive in here. This particular article here from the AMS bulletin is a really great resource of information on the April 27, 2011 outbreak. It goes in depth into what we're going to talk about in this video, which is the environment surrounding the meteorology surrounding the outbreak. But it goes through the chronology, some of the damage, and a lot of the impacts from this event. So if you're looking for a more in-depth publication that is going to go beyond what we're going to talk about in this video, this is a really great resource. I'm going to put the link to this article in the description below. So let's go ahead and get started here. And once again, this is just the Alabama portion of the event. You can see many of these tornadoes were very strong and long track tornadoes. You can see the very long tornado tracks there. And the story of this event is going to start all the way back a few days earlier. So we're going to start here. This is April 24th, 2011 here. So 3 days before the event. We're going to go all the way back there and kind of trace the synoptic pattern back here. So let's go ahead and look here. This is the 500 millibar pattern on April 24th. And you can see fairly zonal flow, but you can kind of see this trough start to transition in to the western half of the United States here. And as we go forward in time over the next couple of days, that trough really starts to dig in. But you can see it is an absolutely massive trough. You can see it extends basically throughout the entire United States. A general rule of thumb when we're looking at determining how quickly a wave pair, a ridge and a trough, is going to move is by the distance between that peak of the ridge and the base of the trough. And a general rule of thumb is when you have that distance between those two is significantly less than the size of the U.S., it's going to move pretty quickly off toward the east. But when it starts to that wavelength starts to increase, it's not going to move a whole lot. So we can see here, this is the axis of the trough, and the ridge is not even on the picture. The top of the ridge is not even on the picture. So this is a pretty massive long wave trough here. So this was not going to move anywhere. And April 27th, as you may know, was part of a multi-day severe weather outbreak, tornado outbreak specifically, that started out across the southern plains and just kind of moved its way slowly east toward kind of the Arklamis area, and eventually on April 27th and 28th into the southeast and eastern seaboard there. So this big old trough was not going to move anywhere very quickly at all. And that's why we were able to sustain rounds and rounds of convection here. You can just see as we go through toward the 26th and 27th that this trough is just absolutely sitting there. It is not moving at all. But we have these little short waves embedded in the flow that really helped kick off these rounds of severe weather. Numerous little short waves, little kinks in the flow that were sort of, as we say, little engines that were able to locally increase vorticity, advection, and lift out ahead of them to produce storms, significant severe storms in those locations. And we'll talk more about that as it pertains to the 27th here in a second. So we are going to start on the evening of the 26th. So this is the evening of the 26th. This is a kind of broad scale radar view. You can see multiple tornadic supercells ongoing across parts of northeast Texas into Arkansas. And as we go throughout the night, these storms congealed into a massive QLCS with lots of little kinks in the line here, almost a line echo wave pattern type deal, where you have multiple sort of waves in that pattern, lots of kinks here in this QLCS that were tornadic and produced tornadoes. And this was initiated here. We'll go toward our 500 millibar map again. You can see once again that big long wave trough here. Nice short wave here, and we'll go down to 700 millibars, and you can see it a little bit better here. So here's 700 millibars, and you can see a very, very well-defined short wave. This is at, let me get the pin off there. This is going to be at 1Z, so you can see a very, very well-defined little shortwave embedded in the flow that really helped initiate thunderstorms there across northeast Texas into Arkansas. And as the night moved on, the forcing became a little bit more linear in nature. We had a very strong increase in the low-level jet. You can see here that is going to be 45, 55, 60 knots here of flow out of the south and southwest here across the region. That allowed storms to really organize into a line segment as forcing kind of was focused very strongly in this region. So we were able to get a very strong QLCS to develop because of that. And this initial QLCS was able to organize throughout the overnight and early morning hours as it moved through Mississippi and Alabama, producing several tornado reports. You can see right in here a little sort of embedded vortex there. And let's go ahead and zoom in here to the radar imagery. We'll go through time here, and you can see, we go forward here, this QLCS is going to really make its way into Mississippi and Alabama. Very, very strong. You can see a very strong vortex there start to wrap up just to the south of the Huntsville area there, and this produced tornadic activity, and there was lots of tornadic activity on the line. And this was, I wouldn't say it was not forecast, but the intensity of the line, and we're going to talk about this secondary area of convection here that produced another QLCS. The intensity of both of these lines were kind of caught meteorologists a little bit off guard, I think. And there was lots of tornado damage and straight line wind damage across Mississippi and Alabama from these storms, and that would create problems later on that day across the region because power was knocked out. and that made it with an impending, very dangerous situation on the 27th, upcoming the afternoon of the 27th. That made it really difficult and perhaps problematic to get warnings out for the afternoon supercell event. So now we see this secondary area of convection fire up across northeast Texas and southwest Arkansas once again. These storms were very much elevated in the wake of that first QLCS. We'll take a look at the surface map here. This is at 8Z, about the time as those storms fired up. You can see that the air mass behind the initial QLCS was quite stable. You can see temperatures in the low to mid 60s out in here, and that's really stabilized the atmosphere. So the main threat with these storms was large hail and damaging winds, and they would quickly, and these were forced by the low-level jet, warm advection atop this kind of cold pool. So you had your boundary kind of right in there, and you had very strong flow over top of this cold pool that was able to force lots of storms to go in that Texas, that kind of Ark-La-Tex region. And we got elevated storms to fire, and there was a severe thunderstorm watch issued for these, and they quickly organized into a QLCS as well. You can see very quick transition to a QLCS throughout the early morning hours. You can see that first QLCS moves off toward the east into Georgia, eastern Tennessee, and Kentucky, starts to weaken a little bit, and then this one kind of takes over. And this second QLCS would have a major impact on the environment for the afternoon of the 27th. So we'll go on here. You can see that the radar shows that QLCS and some activity behind it kind of puts out, you can kind of see the radar reflectivity gradient, at least there. To the south here of this kind of pink line there, we hadn't had anything all morning after that first QLCS. So this atmosphere was very much ready to destabilize, and in fact already destabilized quite a bit by the late morning and early afternoon hours. And if we go forward in time here on our surface chart, let's go ahead and go to 16, let's go to 18Z here. So this would be just after lunchtime, about 1 p.m. on April 27th, and you can see where that outflow boundary was sitting. So there was a very well-defined outflow boundary here from basically far southern Tennessee in through northern Alabama and into northeast Mississippi. You can see temperatures in the 60s, the low 60s, even upper 50s up here in northeast Mississippi, northwest Alabama, and a very potent, very moist, unstable air mass to the south of that. Temperatures in the 80s with dew points approaching the upper 60s into the 70s here, just south of that boundary. So this was concerning. As we know, outflow boundaries, number one, are going to focus lift along them to perhaps initiate storms along them. And any storm that would interact with this boundary, you can see that the winds were very much backed toward the north of that boundary, out of the kind of east-southeast, whereas we had very nice southerly winds to the south of that. So very much enhanced low-level shear in an already very highly sheared environment that was going to be problematic later on this afternoon. Let's take a look at how highly sheared this environment was. So we'll go back to our 500 millibar map here, and we'll go through. So this is 8Z, 9Z. This is at 12Z on the 27th. So this would be 7 a.m. on the 27th. And you can see here, the checklist I have when I'm looking at setups in the southeast, at least tornadic supercell setups in the southeast. The two things I look for are, number one, more zonal or westerly flow in the mid-levels, specifically at 500 millibars, and the presence of an elevated mix layer. So you can tell from this 500 millibar map that we're checking that first box pretty clearly. Very much a westerly component to the flow here at 500 millibars. And what that does is, what that tends to do in these southeast kind of setups is it tends to allow for a more discrete storm mode. And we'll talk about the EML in a second, but I always look for that kind of zonal flow when I'm looking at southeast setups for tornadic supercells, and this definitely fits that bill. Very nice zonal component to the flow here. Very strong jet streak rounding the base of this trough, 80, 90 knots plus jet streak rounding the base of this long wave trough here. And you can just see what it's going to do as it approaches the region. So this is at 18Z, and this is about as textbook as it gets. Again, very, very big long wave trough here. Just an absolutely textbook jet streak here rounding the base of that trough, just pointing a fire hose right at the northern half of Mississippi and Alabama for the afternoon event. Let's go down here and look at our short waves here at 700 millibars. And I mean, I think a 2-year-old could figure out the short waves here in this configuration. Just an absolutely textbook setup here. So you can see lots of different short waves here. There's, in particular, this one right in here. It may have been convectively enhanced a little bit by that secondary QLCS. That first one likely it may have been this one in here that had kind of lifted off toward the north and east. This one back in here was helping to maintain that second QLCS there across northern Mississippi and Alabama in the late morning, early afternoon. We go on a little bit farther, and then our main shortwave, the main crux of this sort of event, starts to rotate into the region by 18Z or so. Little kink right in there as well. So again, this is at 19Z, and you can see the main shortwave is really starting to impinge into the region, and that was what would start to set off storms here across much of Mississippi. Perhaps this little shortwave here in Alabama helped get things going there as well. And we'll talk about the low levels in a second here. Let's go down to 850 millibars as well. You could see kind of just a textbook depiction of a low-level jet here. Very strong mass response from surface cyclogenesis, and again, we'll look at the surface map in a second. But very strong low-level jet in place throughout the morning and afternoon hours. This is 60, 70 knots of flow out of the south-southwest, and that would maintain itself throughout the day and even increase throughout the afternoon as the event really got underway, really helping to enhance those wind shear profiles in the atmosphere. So let's go down to the surface now and kind of go through the progression here. So this was the evening of the 26th. You can see kind of two surface lows here, one up here across the Great Lakes region and one down here in central Texas. Here, this kind of warm front, dry line situation here helped initiate storms on the 26th that would form into that overnight QLCS. Then we would continue to get surface low development because we just had such strong divergence aloft. Again, that's the spreading of those wind vectors aloft. If we take a look at the 300 millibar map here, which is what we like to use for diagnosing divergence here. And again, we got kind of renewed surface low development here as that jet streak really moved in. You can almost see it better at 500 millibars, but this will do. You can see the winds here across kind of northern Arkansas there. And we really start to have westerly winds out here across the Louisiana-Mississippi region. Just absolute textbook divergence aloft there, defluence, the spreading of those wind vectors there across the region. Again, I think you can see it a little bit better at 500 millibars here as that jet streak really starts to nose in. Yeah, I mean, just take a look at that. I mean, as a meteorologist, knowing what happened on this day, really, it's a somber event to talk about. But from a scientific perspective, this is just about as textbook as it gets, and something that really, piques my interest when I see something like this from a scientific perspective. Just look at the amount of divergence here aloft. The winds over Mississippi out of the west-southwest, whereas we have a more south-southwest kind of flow here at 500 millibars across Arkansas. And that divergence aloft, again, creates kind of a vacuum effect. Those winds spread apart aloft, and the atmosphere tries to fill that, and we get rising motion. We get surface low development where that divergence aloft is enhanced, and that's exactly what we got across this region throughout the morning and early afternoon hours of the 27th. We got renewed surface low development here across kind of the Arklatex region into Arkansas, and that would kind of deepen throughout the day and really initiate that mass response out ahead of that, which helps strengthen the low-level jet and really rapidly recover the atmosphere behind the morning QLCSs there across Alabama. Take a look at our temperature and dew point plots here. You'll notice that the bright green and yellow contours are kind of confined here in the early morning down to the Gulf Coast region there. But notice, due to the mass response, how quickly those recover northward here. By the afternoon, those bright greens by 18Z1 just after lunchtime, as the event was about to get underway, those have already retreated northward to the northern half of Mississippi and Alabama there. So very quick recovery of the atmosphere in the wake of those early QLCSs. And by about noon, 1 o'clock, the event was really ready to get underway as that main shortwave nosed in. And we'll take a look here at the satellite imagery as well. We already saw, it's very hard to see on the surface map here, but oftentimes in these sort of bigger days in the southeast, you'll have what are known as kind of confluence bands. These little sort of very weak convergent zones where the flow kind of very lightly comes together. And that's just enough subtle forcing often to fire storms in kind of a broken band here. You can't really see it on the surface map here, but we can really see it on the satellite imagery. And, just a quick note here before we look at the satellite imagery, just look how juicy this environment is. 83/69 here at Tuscaloosa, 81/72 at Columbus, Mississippi, 83/72 at Meridian, Mississippi. That is just absolutely juicy air. Once again, to the south of that outflow boundary that was modifying as that atmosphere and kind of retreating northward as that strong mass response was kind of helping to advect this very juicy air to the north. But just keep in mind for later on that this outflow boundary is going to play a huge role in the event there across northwest Mississippi into northeast Mississippi and northwest Alabama, excuse me. Back to the satellite imagery here. So this is going to be at 16Z, and we go forward in time, and you can just see the confluence bands here. One thing to note, here is our initial, our secondary QLCS here. It's this big blob right in here. And notice at the southern end of that, you can see the actual outflow boundary. Here, you can see this kind of fine line right in here, just to the south of the main area of convection. So that is our outflow boundary, and you can see a number of little confluence bands here across Mississippi and Alabama on which storms would fire. Here's our main frontal zone back in here. If we take a look at the surface map once again, we can see exactly where that frontal zone is. So this is at 18Z. We kind of look for the pressure tongues here. So very much a dry line, kind of pseudo dry line type feature here. Cold front dry line kind of, feature in here. So there's our main boundary. And we're looking well out ahead in the open warm sector here for these confluence bands. And you can see a number of them. So here's the main front well back out in here. You can see one right in here. You can see the cumulus starting to bubble along that. You can see one right in here. You can even start to kind of make one out right in here as well. Here's that outflow boundary once again. And this is where the first major storm of the day in Alabama would come from, this confluence band right in here. It would be the first tornado of the day, first major tornado of the day in Alabama, the Coleman, Alabama tornado. You can see it fire up right there, kind of maybe along that subtle sort of confluence band right in there. But you can see back here, here's a confluence band, just a number of these very subtle confluence bands where the winds are just converging enough to very subtly force these storms to go. And in our last video on the channel, we talked about storm mode. These boundaries oriented basically north-south, and the forcing is already subtle. The jet streak is kind of back in here. Even the main jet streak is back in here, just kind of barely impinging into the region. So the forcing out here is subtle as is. So that's going to favor a discrete storm mode already. And let's take a look at our shear vectors here. So keep in mind the orientation of those confluence bands. Oops, let me go back to the 0 to 6 kilometer shear vector here. So we'll go to 18Z here. So our confluence band's oriented basically something like that. And notice these shear vectors are, this is about as textbook as it gets for discrete storm development. If you recall in our last video, we looked for the orientation of the shear vector with respect to the initiating boundary. In this case, the initiating boundary is going to be those confluence bands. And we want to see that kind of just nice sweet spot in the angle between the 0 to 6 kilometer, the deep layer shear vectors, and that initiating boundary. And we want to have subtle forcing. And we got exactly that. Just as the jet streak was starting to impinge in the warm sector, very subtle forcing along these confluence bands. This was a very clear indication that we were going to see a discrete storm mode. And in this kind of environment, when you have southeasterly surface winds, southerly or south-southeasterly surface winds, a very potent low-level jet out of the south-southwest and flow aloft at 500 millibars out of almost the due west, you're going to have a recipe for some significant severe weather, particularly tornadic supercells here. Let's talk about the EML real quick. I mentioned it earlier. I like to look for an elevated mixed layer, and we'll look at the soundings here in a second to confirm here. But notice where our low-level jet is coming from, and particularly our westerly flow at 500 millibars and our kind of low-level jet out of the south-southwest here. What is that going to do? Well, it's going to draw air in from out in here. And this is late April out in this region, out in the desert southwest, western Mexico. It's going to be pretty warm out in here. So what the more zonal flow is able to do is it's able to pull this nice, dry, well-mixed air from the desert southwest and western Mexico and advect it out into the region. So we have a nice cap on the atmosphere that would help keep any morning convection, kind of crapvection that would interfere with the kind of pristine environment later on, and perhaps temper the severity of the event to some extent. And that's a lot. And you may be saying, well, you need to have more zonal flow and an EML for any setup, and that is true. But I look for them specifically in the southeast setups, because I think we often see these southeast setups and we see these just massive parameter spaces, very high instability, extreme wind shear profiles, and you automatically think, oh, significant tornadoes are a great possibility. Well, that's not always the case if you don't really have these two. Number one, if you don't have a discrete storm mode and you have a very extreme parameter space, you're going to have some tornadoes, but you're most likely to have more embedded tornadoes and more of a damaging wind threat in a kind of more linear storm mode. And when you don't have an EML to deal with, you're going to have storms blow up in the morning that are going to interfere with that pristine environment, and you're going to have too many storms go up at once, and the mode is just going to be overall very, very messy, and that may temper the tornado threat as well. And this case absolutely check these boxes. So let's take a look at some soundings here. We'll start out at Jackson, Mississippi here. This is Jackson, so this is going to be the evening of the 26th. So you can see out ahead of those QLCSs that were going to move their way through overnight into the early morning hours. Nice curvature in the photograph there, very unstable atmosphere there. So there's no surprise that those early morning QLCSs produce tornadoes, some strong tornadoes as well. We will go through here to 12Z. And so this is at Jackson, and by this point, Jackson was situated well to the south of, let me show you the map here, situated well to the south. Actually, let me pull up the radar here. Jackson was situated well to the south of the morning QLCS. So you can see it was impacted by the first QLCS, but well to the south of that secondary QLCS. So it was already recovery was well underway by the 12Z sounding here at Jackson, Mississippi. And that's why you saw such strong wind profiles here and a very unstable atmosphere to begin with here at Jackson. And we'll take a look at Birmingham now. So this is the observed sounding at Birmingham, 0Z on the 26th. And here's at 12Z on the 27th. The first QLCS had just moved through, so it had sapped the instability and made a very, very wonky wind profile. You can see the winds here in the low levels, very, very wonky. But as you go to 18Z, you can see how rapidly that atmosphere recovered. Again, this is at Birmingham, the observed sounding. Very unstable environment, 2,000 joules per kilogram of CAPE, and you can see our elevated mixed layer right in here. Very, a very small layer of steep lapse rates, warm air aloft, that really helped to negate any storm activity that fired up behind that initial QLCS. So it really allowed the environment to be pristine. You can see here this photograph is just absolutely nuts. Almost 600 meters squared per second squared of effective storm relative helicity there. Very strong curvature here in the low level photograph there. So any supercell in this environment, and supercells were likely 70 knots of effective bulk shear there. Supercells were a great possibility, right-moving supercells especially, and in this environment, this was absolutely a red flag for significant, long-tracked, violent tornadoes in the afternoon. And we'll go to Jackson there as well. The profile out to the west, winds maybe started to veer a little bit more quickly here. You can see some curvature there in the low levels. This doesn't mean a whole lot in the southeast. You might see this in the plains and say, oh, well, the winds are really veered in the low levels there, but notice our low level jet is still upwards of 50 to 60 knots here at about a kilometer off the ground. So this doesn't really matter here. This was very extreme low level shear for supercells to work from there at Jackson. Now let's take a look at kind of a higher resolution view here. We'll take a look at the RUC model, and this was back then this was the equivalent of today's rapid refresh model. So a higher resolution model, at least temporally, in a time scale it was able to tell us kind of the initial conditions here. And this was the 18Z run right before storms started to really get going here. This was at Jackson. You can see maybe even a little bit more favorable look than the observed sounding showed. The cap had pretty much fully eroded here at Jackson. Very strong low-level instability there. A deep, deep moist layer there, extending all the way up almost to 700 millibars, which is pretty insane. Very strong instability, over 3,000 joules per kilogram of CAPE. And this was absolutely a profile for significant tornadoes. You can see down to the east a little bit at Meridian, Mississippi. Much of the same, deep moist layer, very strong instability. And I mean, just look at that photograph there. Any supercell in this environment would produce, any discrete supercell would produce strong to violent tornadoes with over 600 joules per kilogram, or meters squared per second squared, of storm relative helicity. Let's go to Tuscaloosa, more of the same. Cap maybe had struggled a little bit, wasn't quite eroded yet. You can see just how juicy the air mass is here across Mississippi and Alabama. 77 over 70 here at Tuscaloosa. Very unstable environment. 2,500 joules per kilogram of CAPE. And I mean, this photograph deserves to be in a museum here. Over 800 meters squared per second squared of storm relative helicity. And that's what happens when you have strong surface winds out of the south. Very, very strong low-level jet, given that mass response as cyclogenesis occurred there in the afternoon. 1 kilometer winds approaching 60 knots here out of the south-southwest, with winds at 500 millibars almost out of the due west. That's going to be a recipe for some pretty significant tornadic supercells there. Birmingham, this was the Birmingham sounding here, and you can see a little bit of a convective feedback here. Not sure why the model was depicting convective feedback there, but you can see much of the same. Extremely deep moist layer, very unstable environment, huge photograph there. This was at Centerville, much of the same. And you can see now these are going to be north of the boundary. This is Columbus Air Force Base, Columbus, Mississippi. And you can see that the temperatures are much cooler up here. But they were starting to recover, and this just north of the boundary, you can see how strong the shear was just north of the boundary. 1,200 meters squared per second squared of effective SRH. Just you can't even fathom a photograph like this in this kind of environment. I've seen these kinds of photographs in just simple warm advection regimes where you have no instability, but you have really strong mass response, maybe a southerly flow off the Gulf. veering to southwesterly flow aloft. You never really see instability associated with them. This was an absolutely scary situation if you were to see this on your model forecast soundings. Again, just north of the boundary there, but it was in the process of recovering, and you can see how the shear would be enhanced along that boundary. Once again, here is at Huntsville, much of the same, over 1,000 meters squared per second squared of SRH there. So we go on through the afternoon, and these confluence bands are going to really start to fire up discrete tornadic supercells as we went on into the early afternoon hours. So you can see here, first storms to fire up were these ones here across western Mississippi into parts of central Mississippi as well, near the Jackson area. And these would move off, again, along those confluence bands, move off toward the northeast into an absolutely pristine, untapped environment here to the south of the early morning outflow boundary from those early morning, that second QLCS. And you can see how rapidly these storms formed into supercells with significant tornado potential in that kind of environment. So we'll go on and look at the soundings here one more time. We'll go to Birmingham here at 0Z. This was the observed sounding at Birmingham, and that's pretty good. Very significant veering of the winds in the low levels. Completely unstable environment here, and you can pretty much see all the composite parameters were absolutely maxed out here. One thing to note, this was mostly a tornado event and not so much a large hail event. And you might be thinking, well, that's kind of weird, but if you think about it, you haven't heard anything about the large hail from this day. It's a tornado event. And that's because we have learned through some new research now, particularly by people like Cameron Nixon, who is, again, a master at looking at photographs and relating them to different severe weather environments. He's been looking at hail recently and has shown that hail tends to prefer much weaker low-level shear. Even though we have very, strong instability here in the hail growth layer, so to speak, very steep lapse rates aloft. Because we have strong shear, and I won't get into the details of it now, that's for a separate video, but again, large hail tends to favor very weakly sheared environments, and you can see that this environment was anything but weakly sheared. This very strong shear environment was going to be more of a significant tornado threat than a large hail threat. So again, back to our 0Z soundings here. This is at Birmingham. Again, over 3,000 joules per kilogram of CAPE. Again, this is the observed sounding. Extremely strong wind shear profiles. 84 knots of bulk shear, almost 600 meters squared per second squared SRH there. And you can see why those storms, particularly these storms down here, moving toward Tuscaloosa and Birmingham, the infamous Tuscaloosa-Birmingham EF4, Philadelphia, Mississippi EF5s, and these ones up here. Now these storms up here, you can see are all supercells. These were very, very close to that boundary. If we go back to our surface map here, let's go back to our surface. Yep, so we go throughout. This is at 20Z. You can see exactly where those storms are. We're reporting thunderstorms at Tupelo and Columbus, tornadic supercells ongoing. We're still seeing that boundary kind of modify a little bit. We'll go toward 22Z. We'll go toward 22Z here. And you can see that the boundary had very much modified in here. You could still kind of make it out in here somewhat. But these storms were really feeding off this outflow boundary here and we're able to track right along it, and in an environment already capable of producing very significant violent tornadoes, this boundary only served to enhance the low-level shear, and that's why we had tornadoes like the Smithville, Mississippi tornado, which was right about in here. The Hackleburg, Phil Campbell EF5 tornado was kind of right in here as well, right along that boundary. The Coleman storm, even early on, as that boundary was a little bit farther south, was able to get very close to that boundary as well. And it was no surprise that the storms down here away from the boundary still produced significant long-track violent tornadoes, because the environment away from the boundary was still upper echelon for significant tornadoes. And that boundary only helped to focus low-level shear, enhance that low-level shear even more than it already was, and produce those significant long-track, some EF5 tornadoes up there in particular. we go on throughout the event here, and we start to see that as that main front moves in, the winds at the surface and in the low levels really start to veer. So the storms that fired up along the main sort of dry line cold front boundary were not as potent tornado producers because the low level shear was decreasing a little bit. But throughout the evening, we did have several significant tornadic storms move off into Georgia. And you can see here, this is just silly here as we go through the radar. Just such a discrete profile here, discrete storm mode in a very strongly unstable and strongly sheared environment. And these storms just lasted forever. This particular storm that produced the Tuscaloosa-Birmingham tornado, the EF4, it started all the way back here, and I'm going to pull up the radar view here, and we'll trace this one back in here. So here's our Tuscaloosa-Birmingham storm, right in here. So we'll trace this storm back here. Keep an eye on that particular storm. Notice that it fires up to the southwest of Jackson, Mississippi. And keep an eye on this area. It's going to track all the way through Birmingham, Tuscaloosa, Birmingham, toward the Anniston-Gadsden area. It's going to continue producing significant tornadoes all the way through into Georgia, even into far southern southeast Tennessee. You can see it just keeps on going and going and going and going and going and going, and finally dissipates as it gets up there into far southeast Tennessee, almost toward the Carolinas. That's how supportive this environment was for very, very strong long-track tornadic supercells. So as we go throughout the event, we'll just kind of finish the radar look here. You can see, just a number of tornadic supercells here continuing on throughout the day. Multiple strong tornadoes. And they just kept on chugging their continued development down there across eastern Alabama into Georgia. And then finally our last round was kind of this on the main boundary back here, moving through central Alabama throughout the evening. So that kind of does it for the main portion of the event, and it just shows you that the ingredients really need to be perfect for an event like this to take place. We had a very, very much a discrete storm mode that really, really helped storms stay supercellular and isolated, and that is always going to up the significant long-track tornado threat versus a more linear configuration to the storms. We had that very nice, shear vector orientation with these weak sort of confluence bands oriented kind of like this, shear vectors like this, already subtle forcing in the warm sector out ahead of the main boundary well back in here, and that was going to be a recipe for discrete storms. We had, of course, your classic, southeast parameter space that was off the charts, and this one, of course, was upper echelon, 99th percentile type stuff. You're not really going to see this that often ever again, but profiles like this you just don't see that often. We see this in the southeast quite a bit. Strongly unstable, strong shear, and that is all well and good, but the one thing was, again, the discrete storm mode and the elevated mix layer that was able to hold off all storm development here south of that secondary QLCS, behind the initial QLCS, that was able to really allow that environment to be pretty much untapped and just be an absolute powder keg to be able to produce discrete supercells to act on the extreme parameter space that was in place. And this was just one of those events where all these things kind of came together in harmony, in perfect harmony, to produce a very, very significant tornado event. So let's go ahead and round out this discussion here by looking at what was the bar for super outbreaks, tornado outbreaks before this 2011 event, and that was the April 3rd and 4th, 1974 super outbreak. You can see here in this paper by Corfiti et al. This was a significant outbreak. This was Ted Fujita's diagram of all the tornado paths from this event. And you can see we had 148 tornadoes in 24 hours from April 3rd and 4th, 1974. One thing that makes the April 27th, 2011 event so much more impressive is you can see how wide of a swath that all these tornadoes occurred within here in this 1974 outbreak, from southern Michigan all the way down to the south into southern Mississippi. Whereas in the 2011 event, we'll go to our paper here, zoom in, you can see how confined the area was here, just in this part of northern Mississippi, northern Alabama, into northern Georgia, into eastern Tennessee, really, at least on the April 27th portion of the event. So a very, very concentrated, focused area for strong, significant, long-track, violent tornadoes on the April 27th event. And whereas in our 1974 event, the ingredients were there across a much wider swath and produced tornadoes across a much wider swath as well. So let's go ahead and take a look here at comparing the two events. So again, we'll go back to our 500 millibar map for our April 27th event here. So we'll go to, let's say, 18Z on the day of. You can see just that textbook look. Of course, more zonal flow here, more westerly sort of flow here at 500 millibars. Very significant sort of jet streak here, rounding the base of the trough. Very long wave, very big trough here across almost the entire U.S. Well, no surprise that this was our April 3rd, 1974 500 millibar map at 18Z, and I'm using Tornado Archive here. Great website here for looking back at significant tornado events in the past. And what do we see? Much of the same thing. This huge long wave trough here across almost the entire continental U.S. Centered a little bit farther south maybe here, but the overall idea is the exact same. Very strong jet streak rounding the base of this overall trough. A little bit farther north of an ejection of that jet streak, and maybe a little bit more meridional flow component to the flow here for this April 3rd and 4th, 1974 event. But you can see here it's almost identical as far as at least the general pattern goes. Very big long wave trough, very strong jet streak rounding the base of that trough, just pointing a fire hose at the affected areas here. It's very strong divergence aloft, diffluence of those wind vectors aloft there. And you can see here much of the same. I mean, this is just another textbook example of divergence aloft here. You can see the diffluence here in the wind vectors here across this region, and this was the region that was going to be most under the gun, the Indiana, Ohio, Kentucky, for strong, significant tornadoes that afternoon into the evening of the 3rd and 4th here. Very similar pattern. We'll go to let's go to our 850 millibar map here, see what we see, and you can see a very intense cyclone there as well. We'll go to our 850 millibar map for our April 27th event, and you can see much of the same. That mass response here. We'll look at the surface low once again here in a second. Very strong mass response from surface cyclogenesis there, and a very strong low-level jet here. Much of the same idea, just a little bit displaced a little bit farther north and across a little bit wider of a swath here, but very strong, 60 plus knot, 50, 60 knot plus low-level jet here across the region east of that low-level cyclone. We'll go down to the surface map here. We'll take a look. Let's actually take a look at dew points here as well. Now, this was a little bit more concentrated of a surface low here in the 1974 event. You can see kind of one main surface low, very potent surface low that was able to really draw that moisture north, create that mass response as you went throughout the day. And as we circle through, you can just see that kind of one surface low really start to eject off to the northeast and continue to pull that moisture northward as it deepened. The April 27th case, not as much. We kind of had those two different surface lows, but really it's the same idea. You can kind of see the two different low centers here. One across the Great Lakes region here, one across the southern portion of the outbreak area. And we actually had tornadoes all the way up here into the northeast. But you can see much of the same thing. Just we were able to kind of focus the mass response in the very favorable overlap of ingredients across a very small, relatively speaking, area of kind of the northern half of Mississippi and Alabama into far southern Tennessee, east and southeast of that well-defined surface low there across Arkansas. So once again, you can see the similarities with this event. And one thing that is kind of difficult to ascertain was, kind of the storm mode and the degree of the elevated mixed layer here. But what this kind of more zonal flow aloft does is it helps pump in that moisture, or that drier, warmer air here from Mexico, from the desert southwest into this region, to really help put that EML in place and hold off convection for much of the day. Yeah, so here's our satellite imagery. And you can see this is another absolute textbook look here. This is our visible satellite imagery from April 3rd, 1974. And you can once again really see these confluence bands taking shape across the open warm sector here. We go throughout, you can see a little bit more maybe of a kind of more banded sort of storm mode rather than the kind of pockmarked, discrete kind of randomness to the storms in the open warm sector along those random sort of confluence bands. Maybe a little bit more sort of well-defined banding here, but these shear vectors were definitely going to allow storms to remain at least semi-discrete, and that was one factor that was very, very similar as well to the April 27th event, was that we had more of a discrete to semi-discrete storm mode here maintained throughout the event on April 3rd and 4th, 1974. You can see it there across Alabama and Mississippi as well. You can kind of see the evidence of the discrete mode there, more cellular sort of convection you can see there. And of course, it's going to be tough to see on a satellite imagery because the anvils are going to kind of spread into one another here. But you'll have to take my word for it, the mode here, and if you read the article here by Corfidi et al., you'll find out that the storm mode was very much discrete here for the April 3rd, 1974 event as well. So that's going to just about do it here. That hopefully gives you a really nice perspective on just how impressive this April 27th, 2011 event was over a very relatively small spatial sort of domain here. We had the pretty much absolute perfect setup for strong long track, a strong tornado outbreak. Everything was kind of maxed out. Of course, we know the ambient environment was, pretty much, this good from the get-go, very strongly unstable, very strongly sheared, already supportive for supercells because we had, that more zonal flow aloft, that elevated mixed layer coming in from the west to help hold off convection after that initial round of storms in the morning. Very strong shear, very strong cyclogenesis there, promoting that mass response. Very strong low-level jet here atop, southerly surface winds, strong southerly surface winds, and that was going to, make for a very impressive event already. You had other things like, of course, the topography in the southeast. There's some evidence that tornadogenesis was supported by some of the more mountainous terrain out here as well on the lee side of the big mountains. And they discuss it here in this paper by Nupp et al. Again, I'll put the link here in the description below, that the topography may have played a role. And again, that outflow boundary across northwest Alabama helped to even further enhance low-level shear to produce those, notably the Smithville, Mississippi, and Hackleburg, Alabama EF5s up there. But again, the atmosphere was absolutely primed, pretty much pristine as far as tornado outbreaks go across a pretty small region here for the April 27th outbreak. So that'll just about do it. Thanks for watching, and we'll see you in the next video.